In this video, we're going to give a high-level overview looking at the primary dimensions of this technology that we call the blockchain. We'll first talk about the underlying technology, then the distributed ledgers that this technology supports, then the token economies that can be built on top of that ledger system. We'll only touch upon these topics here to get an overview before going into them in more detail in future videos. On its most basic level, the blockchain is a new class of information technology that combines cryptography with distributed computing, both of which have existed for a number of decades. It was the genius of Satoshi Nakamoto to combine them in new ways, to create a model where a network of computers collaborate towards maintaining a shared and secure database. As such, we can say the blockchain as a technology is simply a distributed, secure database. This database consists of a string of blocks, each one a record of data that has been encrypted and given a unique identifier called a hash. Mining computers on the network validate transactions, add them to the block they're building, and then broadcast the completed block to other nodes so that all have a copy of the database. Because there is no centralized component to verify the alterations to the database, the blockchain depends upon a distributed consensus algorithm. In order to make an entry onto the blockchain database, all the computers have to agree about its state, so that no one computer can make an alteration without the consensus of others. Once completed, a block goes into the blockchain as a permanent record. Each time a block gets completed, a new one is generated. There is a countless number of such blocks in the blockchain, all connected to each other, like links in a chain, in proper, linear, chronological order. The blockchain was designed so that transactions are immutable, meaning they cannot be deleted. Each block contains a hash value that is dependent upon the hash of the previous block, so they're all linked together, meaning if one is changed, then all the other blocks linked to it going forwards will be altered. This works to make the data entered tamper-proof. What we've described here is the workings of the first generation of blockchains, which function largely simply as databases. But the technology is currently evolving to become much more than this, as the second generation already provides the capacity to execute any computer code on the blockchain. The system is evolving to become a globally distributed cloud computing infrastructure. And as we'll discuss in a future video, it remains very much a work in progress when seen from this perspective. Blockchain technology works to create a permanent and secure database. This makes blockchains suitable for the storage of a record or transaction that involves value or in some way needs to be a secure and trusted source of information. These secure, distributed records are called distributed ledgers. A distributed ledger is a consensus of replicated, shared, and synchronized digital data geographically dispersed across multiple sites, countries, or institutions without centralized administration or centralized data storage, being maintained instead by a distributed network of computers. Such ledgers can be used for any form of asset registry, such as inventory or monetary transactions. This might include the recording of hard assets such as physical property, cars, homes, etc., or intangible assets such as currencies, patents, votes, identity, healthcare data, or any other form of valuable information. This distributed ledger technology enables us to replace a multiplicity of private databases within each organization with one shared database that is trusted and accessible by all parties involved. In this respect, the blockchain enables trust between parties that may otherwise not trust each other. The results greatly strengthen our capacity for collaboration between organizations or between individuals peer-to-peer, without dependency on third-party centralized institutions. Likewise, they result in transparency and many other efficiencies. This is of major significance, as we currently have many centralized organizations that may be internally optimized, but the inter-organizational space in between them is really inefficient, with huge amounts of border friction, redundancy, arbitrage, and resources wasted on competition. By enabling trusted inter-organizational networks, these ledgers enable the formation of organization and collaboration where previously there was none, such as across whole supply chains, or for different healthcare providers to collaborate around the patient's needs, or for different transport providers to collaborate in delivering an integrated logistics network. Likewise, second-generation blockchains offer the possibility to automate the workings of these networks through what we call smart contracts. Smart contracts are computer code that is stored inside a blockchain, which encode contractual agreements. These smart contracts are self-executing contracts, with the terms of the agreement or operation directly written into lines of code, which are stored and executed on the blockchain. Like normal computer programs, these containers hold algorithms that take an input of data and, depending on the value of the input, trigger certain events. For example, this might be a financial contract that takes as the input the amount of money in a person's account. If it is above a certain level, then it increases the interest rate that they earn on their deposit. Such smart contracts can be used for automating many basic operations on the network, once again working to remove the need for intermediary third-party institutions, as smart contracts can be trusted, are tamper-proof, and execute automatically. Much of the current discussion surrounding blockchain remains at the level of the technology and the possibilities of distributed ledgers, as a shared, trusted database enabling the collaboration between organizations, with the resulting disintermediation of centralized institutions and market exchanges. However, its implications go far beyond this, as the blockchain concept is more than just a database or ledger. It is a new organizing paradigm for the discovery, validation, and transfer of all discrete units of value, and the development of distributed organizations via token market systems. A token is a quantified unit of value that is recorded on the blockchain. This value may be of any kind. It may be likes on social media, it might be a currency, it might be the integrity of an ecosystem, or it might be an electrical unit. Token networks consist of a network of independent nodes that act autonomously, but through incentive structures and the signaling system of the market, self-organized to create emergent coordination and thus a distributed management system. For example, we might create a clean air token, where anyone who provides a service that contributes to the maintenance and provision of clean air can earn tokens, for example by planting a tree, while those who pollute, by say operating a combustion engine, have to pay in air tokens. Thus, instead of having a centralized authority and a Clean Air Act, we have a token market that works to create signals that align people's incentives with maintaining and growing the underlying resource. Likewise, this same model could be applied to the management of technology infrastructure. As an example, we could think of traffic control. We currently have traffic control systems in cities whose operations are monitored by centralized control centers. But in a world of autonomous vehicles on the blockchain, cars could signal to each other, peer-to-peer, bidding tokens to see which gets priority. In such a way, the system has dynamically allocated resources and self-organized via distributed token networks. In short, blockchain is not just an information technology, but also an institutional technology, in that it enables us to design incentive structures in the form of token economies, and in such a way convert centralized organizations into distributed markets via token economics. This is where things start to get quite complex, as we move into the realm of designing economies and incentive systems for coordinating human activity in a decentralized fashion, something that could potentially enable the coordination of human activity at a much larger scale than has been possible before. The great design innovation of the blockchain is really its capacity to coordinate a network of autonomous nodes towards maintaining a shared infrastructure, and this is done not just through innovations in information technology, but also through the design of incentive systems, which has traditionally been the domain of economics. Through adding a layer of trust and value exchange to the internet, the blockchain merges our newly developed information networks with the institutional structures that sit on top of them. In so doing, it greatly strengthens the capacity of those networks as a new mode for organizing society and economy. By merging economics and technology, it enables us to redesign institutional structures and ultimately reconceptualize how we organize virtually every aspect of society, economy, and even technology infrastructure, based on networks of autonomous nodes that are incentivized to collaborate. Of course, it does not do this alone. Such claims can only be realized in combination with other technologies and broader processes of change. As such, the blockchain has to be understood in the context of a broader set of technological transformations taking place with the current evolution of the internet. Most notably, much of what the blockchain promises will only be possible given parallel developments in the Internet of Things, datafication and advanced analytics, all of which are combining to form the next generation of internet, of which the blockchain will be a critical infrastructure.